Section 4.3 is called stability and the singular value decomposition. But before we start with stability, let me summarize my minimal take-home message from section 4.2. So if A is an m by n matrix with real or complex entries, then we can talk about the singular values of A. And these are non-negative real numbers, and we usually denote them by S little I, where I is running from 1 to m or n, whichever is smaller. And we can express the norm of A in terms of these singular values Si, because we have learned that the maximum of these numbers is exactly the operator norm. Remember, it's the largest radius of the ellipse or ellipsoid on the other side. Okay, next let's look at the inverse of A. And of course the inverse only exists if A is a square matrix of full rank. Okay, but then we can talk about the singular values of this of the inverse matrix, and we can express them in terms of the original singular values of A, and we know that they are just the reciprocals, so they are 1 divided by Si, and we can do that because none of them is 0. Okay, and the norm of the inverse is just the maximum of the singular values, which are now these numbers. And sometimes it is helpful to express that as 1 divided by the minimum of the singular values. So in particular, we see that the norm of the inverse is just 1 over the smallest singular value. Okay, and then finally the more Penrose inverse or pseudo-inverse. Unlike the inverse, the pseudo-inverse always exists for m by n matrices. And we can say something about the singular values, and we just learned this, it's up here. So the singular values of the pseudo-inverse are the reciprocals of the original singular values that are non-zero. And those that are 0 just remain at 0. And let me just label them as Si plus, which makes sense in lots of perspectives. One of them is, okay, the notation suggests that these are the singular values of A plus, but it also makes sense in the following perspective: Si being a number is a 1 by 1 matrix, which has a more Penrose pseudo-inverse, and that is this here. Okay, but now the norm of the pseudo-inverse is just the maximum of these numbers. Okay, we can clearly neglect this case in our maximum and then rewrite like we did here. Okay, excellent, very important table. But now let's go back to infinite matrices A and projection methods AN with finite square matrices AN. Well, at least after a suitable identification, we'll be able to identify our operators AN with finite matrices AN. Okay, and we will look at the singular values and norms, mostly of these matrices, because we are interested in stability, which is connected to inverses and their norms and so on. So recall from Polsky's theorem, our projection method AN is applicable if and only if A is invertible and AN is stable. We will soon learn to adapt the Polsky theorem to the case of a non-invertible A and least squares problems instead of Ax equals B. But for the moment, let's continue to assume A is invertible. Okay, well then, if this condition here is guaranteed, then it's all about checking the stability of your sequence AN. And this table here kind of suggests that we could do that in terms of singular values. So let's try. Well, first let's recall the definition of stability. The sequence AN is stable if and only if there exist N0 and M such that for all N larger than N0 the AN is invertible and the norm of the inverses is bounded by this constant M, capital M, which does not depend on the little n, so it's the same for all. So we often express it in this form: the supremum of all the norms of the inverses is finite, and in this case it's bounded by this global constant capital M. If you want to draw something at this point, then it's probably the following diagram, where you put the integers n over here, and for every integer you mark the norm of the inverse an up here. So stability means there is an integer little n0 and an upper bound capital M, such that the part of our graph to the right of this red line remains below the blue line. Okay, so each one of these n gives you an invertible an, and the inverses do not exceed the blue line. Nothing is said about the n that are less than n0, so that some of them could give you small inverses, some of them could give you large inverses, some of them could give you no inverse at all, in which case we usually say that the norm of the inverse is infinite, which is our code for not invertible. Okay, so this is all fine as long as the graph behind n0 stays in this box. That is, of course, unbounded to the right. Okay, now let's try to express this norm of the inverse of an, which is a finite square matrix, in terms of the singular values of an. We get a sequence of matrices an, and therefore a sequence of singular value sets. Let me abbreviate the set of singular values of matrix A1 by just this. SV of A1 denotes the set of all singular values of A1, and we know that this is a set on the non-negative half axis, and if A1 is just a 1 by 1 matrix, then that's just one number here. Okay, then the singular values of A2, if that's a 2 by 2 matrix, consists of 2 points on the non-negative real axis, and so on. Then you reach n equals n0, which has this many points on the non-negative half axis, and you simply continue like this without end. And now for each of these matrices or operators an, the inverse exists if 0 is not a singular value, so it's not here in blue, and the norm of the inverse is 1 over the minimal singular value. So maybe let's label the minimal singular value by m sub n. So the norm of the inverse of A1 is just 1 over m1, and the norm of the inverse of A2 is 1 over m2, and so on. So now for stability, we need a global upper bound on all these inverses here. And that means these numbers here need to be separated from infinity through a global upper bound. So one that works for all of them. Let's call it capital M. But of course you get this uniform upper bound if and only if your smallest singular values, the one we have labeled in red, are separated from 0 uniformly by a uniform lower bound, which in our case would be 1 over capital M. And actually it's enough to have this only for n larger than n0. So this means no singular values in this unbounded green strip here. So we can drop this condition on the first few n. It only has to hold for sufficiently large n, which means after a certain n0. Let's write this condition down in a more proper language. The sequence an is stable if and only if, and now it starts like before, there exist n0 and m, and these are the same as before, such that for all n greater than or equal to n0, the minimal singular value of an, which is what we abbreviated by mn, is now greater than or equal to some constant, which happens to be 1 over the m from before.